Right, in section 3.2 we'll look at polynomial functions. So generically a polynomial function is written like this. Polynomial with x being the variable is equal to some number in front, which we call an, x to the n, plus an minus 1, x to the n minus 1, plus an minus 2, xn minus 2, plus dot dot dot, plus these three dots mean the pattern repeats. You get to a1 x to the 1, and then you get to a0. So there's no x's now. So this can seem confusing to some students because you have all these subscripts and superscripts. So let's just do a small example. Let's say I have a polynomial, and I'm just going to make these numbers up as I go. So let's say 7x to the 5th minus 3x to the 4th plus 1/2 x to the 3rd plus 17x squared minus 21x, and then we'll say plus 6.5. Okay, so all this pattern says is that an, so an would be 7, so these just match up, and an minus 1 just means, okay, the next x term just has a different number in front of it. So we have 7 and minus 3, and they could actually match, so it might be the case that they're the same number. But generically we write it like this: an minus 1, an minus 2, just to represent how many different numbers we have. Now in this case, n is 5. So that's called the degree of the polynomial. So this is degree 5. And so if you look at this, it goes n minus 1. So 5 minus 1, n minus 1 would be 4. So the next term would be x to the 4th. And then we have n minus 2. Well, 5 minus 2 is 3, so the next term is x to the 3rd. So you can kind of see a polynomial has this decreasing power of x. So x5, 4, 3, 2, 1, and then no x at all, that's called a0. Okay, now the key to this is, for this to be a polynomial, n has to be bigger than or equal to 0 and an integer. And even that, so an integer is no decimals, no fractions. So we can't have the square root of x, we can't have the third root of x, because those are really fractional powers. That's 1/2 and this is 1/3. And we can't have 1 over x, because that's x to the negative power. We can't have 1 over x squared, that's x to the negative 2. So let me do one more. We can't have 3 over x to the 4th, because that would be 3x to the minus 4. So you see that those are all negative powers, and these up here are fractional powers. So this restriction here says we can't have fractional powers, we can't have negative powers. So if I look at this first one, this one's okay, 5x to the 4th, it's positive, it's an integer, whole number 4. This one's okay, 4x to the 3rd, it's positive power, it's an integer power. This one is not okay, so this would be written as 5x to the minus 1, and we can't have those negative powers. So this one, we would say, is not a polynomial. A polynomial has to have positive powers of x that aren't fractions. Okay, for number 2, it's very similar, but I'm going to do one algebra trick, and that is if you have multiple things, if you have two things separated by a plus or minus on top of one thing, you can split it into two things. So I can split this into x squared over x squared, and the minus sign stays, and then I have 4 over x squared. Try to use color here to help you see what I'm doing. So you can actually split multiple things on top of one denominator into the two separate fractions. And what this is going to do is it's going to simplify into x squared over x squared is 1, and then 4 over x squared I'm going to write, similar to an example I showed before, 4, and I can make that x squared flip up next to the 4 if I make its exponent negative. So dividing by x squared is the same as multiplying by x to the minus 2. But now, once I do that, I'm going to see that, we can't have negative powers for a polynomial, so this one is also not a polynomial. Now, it's interesting. If this 1, the 1 is just a number, that's okay. That could still be a polynomial. But when I have an x to a negative power, then it's not. Okay, for number 3, we're going to introduce a new idea. It's called the leading coefficient test to determine the end behavior of the graph of the given polynomial function. So first off, is it a polynomial function? Yes, because the powers are all positive, and there's no fractions, there's no division, there's no square roots, anything like that. So we do have a polynomial. In fact, let's look. It's degree 5. And something about the degree we're going to start to now think about is this even or odd? So notice that that's an odd power. Okay, so we want to look at build a table for this. So let's pick some x values, and then we're going to separate out each of these terms. So we have 4x to the 5th, we have 5x squared, we have minus 7x, and we have 3. And then we're going to sum these terms up because that would be the answer to whatever we're plugging in. So we're going to plug in minus 1, minus 10, minus 100, then positive 1, positive 10, and positive 100. And we're doing this just to prove a point, so we'll see if you can agree with the point we're trying to make. If you plug in minus 1 into 4x to the 5th, you get minus 1 to the 5th, which is minus 1 times 4, which is minus 4. Minus 1 squared is 1 times 5 is 5. Minus 1 times minus 7 is positive 7, and this is positive 3. If you add these numbers up, you get 11. Okay, now try minus 10. Minus 10 to the 5th is minus 100,000 times 4 would be minus 400,000. Minus 10 squared would be 100 times 5 is 500. Minus 10 times minus 7 is positive 70, and this is 3. If you add these up, you get minus 399, minus 399,427. Minus 100, you plug it in, you get minus 40 billion. And you get over here positive 50,000. And over here you get positive 700, and over here you get 3. And hopefully the point's starting to be made. This 400,000 over here does not get changed much by the 500, the 700, or the 3. It's even more pronounced at minus 100. 40 billion does not get changed much by 50,703. So this answer is approximately the same as the first term, minus 40 billion. If you plug in positive numbers, you get a very similar result. You get 4, 5, minus 7, and 3. Those add up to be 5. So when x's are small, these middle terms do affect it quite a bit. But even when I get to 10, I'm going to get 400,000 here. And we're going to get 500 here. And minus 70 now, and 3. And so these will add up to 400,433. But then here I'm going to get 40 billion positive. And then I'll get another 50,000. And then a negative 700 now, and 3. And this 40 billion is not even barely altered by these other terms. So this answer is approximately just the first term, the positive 40 billion. So what we're going to look at here is what we're going to say is the end behavior when x is large. X is large, either positive or negative. So big numbers, either positive or negative. All I'm going to care about is the very first term. So this whole exercise is to argue that these don't really matter to these x values that are so big. So x to the 5th is growing so fast that these other terms can't keep up. They don't really change it much. Okay, with that, once we decide that, then all we care about is the first term. And so let's analyze that a little more closely. So there's 4 graphs I'm going to show you, and you only have to memorize 2 of them. And if you memorize 2 of them, you have the other 2 just by reflection. So if you have an odd power, it will always fall to the left and rise to the right. So this is any x that is odd. And there's one other thing you have to look at. You have to look at the number in front. So we called that in the polynomial a to the n, x to the n. So that's the only term we care about. So a to the n is the number in front. If an is greater than 0, it looks like this. If the number in front is negative, less than 0, it flips this. So where this was falling on the left side, now it's rising on the left side. Where this one was rising on the right, now it's falling. But it's still for odd powers. Okay, and so we're going to put in here, this is falling to the left. This is rising to the right. This one is rising to the left. And this one is falling to the right. Okay, so we have, so this will cover any odd power. So 3, 5, 7, all those odd powers, they all look like this. This kind of sideways S. So we have a positive leading coefficient, and we have an odd power, so it matches this first one I drew, matches this one right here. Positive coefficient, odd power, so it's going to fall to the left, rise to the right, and the best answer for that one is C. So it's going to fall to the left, rise to the right. Okay, now the next problem we'll look at even powers. Okay, so number 4, we have an even power so first notice that these are all in order. So that's a key. So make sure that in a polynomial you write it in descending powers of x. So 4, 3, 1, and then no x at all. And we're going to do the leading coefficient test to test for n behavior again. So the only term we're going to care about is this term right here. Don't care about these based on what I just proved in the last problem. If you built a table of x values and y values, you'd see that those 3 terms at the end aren't going to really affect it much when x gets big. So here's the only 2 graphs we need to know. Let's actually do it down here. We can have the leading coefficient, an, be positive, or we can have the leading coefficient, an, be negative. And these are both x to the even power. And x to the even power will always look like a bowl. So if the leading coefficient is positive, the bowl faces up. If the leading coefficient is negative, it's going to flip the bowl and make it look pointing down. So these both rise left and right. These both fall left and right. So we would have, let's see which one, it would be D. So they fall, oh, well, we forgot to analyze which. So notice this -6 here is going to be this case here. So it's negative and it's even, so they're both falling to the left and the right. Not too bad. Okay, for 5, it's going to get a little more interesting because we're going to look at the n behavior. We're going to start to find the zeros of the function. We're going to do more things. So first off, we're going to notice that this is x to the 3rd. So we have x to an odd power, and the leading coefficient is 1, so that's positive. So we have an is greater than 0, it's 1. So we know the shape should be like the one we started with for n behavior. It should fall to the left and rise to the right. So the overall n behavior should look like that. And now they want us to actually find the zeros. To find the zeros of this, we have to factor it. So you might notice that there's an x in every term. So we're going to factor that out and get each of these powers decreases by 1 now. So 3 becomes 2, 2 becomes 1, and 64 loses its power, its x, because we stole it away. Okay, now we're going to look at the factors of 64. This is the AC method we've been studying. The the factors of this that add to this number, minus 16. And if you look at it long enough and think about it, write down the factors of 64, you will discover that x minus 8 and x minus 8 is the factors. So those two numbers multiply to positive 64, and they combine to be negative 16. And now we're going to, so that's the factored form of that polynomial. Now we're going to set that equal to 0 to find the zeros of the function. So the zeros are when the graph touches the x-axis. Okay? And if we know those, then it really helps us fill in the drawing. So we know the end behavior, it's going to go down to the left and up to the right, but we need to kind of get a sense of what does it look like closer to the crosshairs of the XY grid, the axes. Okay, so to do this, you just set each of these equal to 0. So you're going to say, okay, if this is equal to 0, or this is equal to 0, or this is equal to 0, we're going to get 0 out. So set them each equal to 0. So one answer is x is equal to 0. So that's an easy one. Then the second one is set x minus 8 equal to 0. Add 8 to both sides. The answer is x equals 8. Third one, set x minus 8 equal to 0. Add 8 to both sides. The answer is x equals 8. So you have two zeros at 8 and 8. Now, in your homework, you don't have to record repeated numbers. You just have to type 0 and 8. But I'm writing it this way just so you can see something, that we do have two 8s. So we have two 8s. And if you have multiple numbers, you say that it has multiplicity. So this is multiplicity. And we're going to call it 2 because there's two numbers. So if you happen to have 3 8s, it would be multiplicity 3. If you had 4 8s, it would be multiplicity 4. Now, even though there's not a repeated 0, we're still going to give this a multiplicity. We're going to call it multiplicity 1. Because there's 1, 0. One x value being 0 creates this whole thing to be 0. Two 8s, though, would make this also 0. So we have two of those. So now we have to pick the right answer block. So technically we had two unique zeros. And what's going to happen? So if your multiplicity, let's do a little picture over here. If your multiplicity, you have two options. It can be odd or even. If it's odd, the graph at that 0, so let's say the 0 is right here, the graph will cross at that point. So for odd multiplicities, the graph crosses the x-axis. If the multiplicity is even, then at that 0, so let's say the 0 is here, the graph will actually touch and turn around. So it will come from wherever it is. By definition, a 0 must touch the x-axis, and then it's going to touch and turn. So it touches and turns. I like to say it bounces, but that's not the way they say it in the homework, so I'll match them. Touches and turns. Or bounces off the x-axis. So notice, at this 8, it's a multiplicity of 2. That's even. So it's going to touch and turn. So we're going to say, I guess that we're answering the next question. So let's first put in this one. The multiplicity of the small 0, which is 0, so the small 0 was 0. How many multiplicities? It's 1. Multiplicity of the larger 0, which was 8, it had a multiplicity of 2. Okay, now in the next part, we have to answer if it touches or crosses. So let's answer it here, and then we can see what it looks like in the box below. So this is even, so it's going to touch and turn. This is odd, so when x is 0, it will cross the x-axis. Okay, so let's see how that looks in the actual homework down here. So we get kind of a new blank here. And we're going to say the graph crosses the x-axis. So the answer is going to be B, because we have something going on for both. It crosses when x is 0, the graph touches the x-axis and turns around x equal to 8. So if I were to draw this, and this is the goal, is to get this drawing complete, we had a 0 at 8 and at 0. Now we know from the end behavior, the first drawing I did, that it's going to rise to the right and it's going to fall to the left. And in between those is this behavior that we're talking about here. So at 0, we know it crosses the x-axis, so it's doing something, it's going to cross there. Now, we know it has to come back to the x-axis to touch the 8. So it's going to do something, come back, touch there, but at 8, it's going to touch and turn because it's a multiplicity that's even. It's going to come back up and then reconnect with its end behavior. So the graph's going to look something like that. Okay, that's the tricky part. We're going to have some problems now where we're going to keep growing on our skills to get these drawings. So let's look at the next one. Okay, one of the hardest parts about 6 is just factoring it. So we have this function, and there's no common x to every term. There's no common number to every term. So this we have to use something called factor by grouping, which you would have learned in intermediate algebra. So we're going to separate these two terms like this. And we're going to look at, okay, what's common about these numbers underlined in green. So if you look at those numbers underlined in green, you'll see that they both have an x squared in them. So we're going to factor out an x squared. And what's left? X to the 1 plus 9. So this x cubed becomes x, this 9x squared becomes 9. Now we're going to look at the blue. What's common about those two numbers in blue? Well, they're both even, so you could start by dividing by 2 and just see how many times you can. So keep dividing by 2, keep dividing by 2. Or, a faster way, see if 144 can divide 16. And it can, which means 16 is common in both. In fact, negative 16 is common in both. So let's factor out minus 16. And what will be left is x. So if I pull away minus 16 from this term, I'm left with x. And then minus 144 divided by minus 16, the minuses cancel, and it's 9. So 16 goes into 144 9 times. Now if we've done this correctly, this should happen. These match. So now we're going to factor that out. So we're going to factor out orange. So x plus 9 is common to both. And then we're going to write what's left. So what's left are these two terms, x squared minus 16. Okay, that's pretty close, but we're going to need one more thing. That's something we've studied a few times in this course already. If you have the difference in perfect squares, they factored a plus b, a minus b. So if I have something like x squared minus 16, x squared minus 16 is really x squared minus 4 squared. So this will factor into x plus 4, x minus 4. So this whole thing will factor x plus 9, x minus 4, x plus 4. And now once again we're trying to find the zeros, so we're setting this equal to 0. And so you just set each of these bubbles equal to 0. But there's a shortcut to that. Hopefully you can start to see this. The x that makes this 0 is minus 9. The x that makes this 0 is positive 4. The x that makes this one 0 is negative 4. It's just the opposite of those numbers. So we have three zeros, minus 9, 4, and minus 4. Now notice there's only one of them. So all of these have multiplicity 1. So you look at each 0 and you say, how many of those do I have? You only have 1 minus 9, you have 1 4, and you have 1 minus 4. So they all have multiplicity of 1. So we would say there are three zeros. The smallest 0, which would be minus 9, its multiplicity was 1. The multiplicity of the largest 0, which would have been positive 4, its multiplicity was 1. The multiplicity of the other 0, so the other one we had was minus 4, its multiplicity was also 1. Now, because they all have multiplicity 1, which is odd, all of these will cross the x-axis. Oh, and let's also point out that the largest coefficient, the largest degree is 3, and it's a positive an, so again it's an greater than 0, and x is to an odd power, so the end behavior should be falling to the left, rising to the right. So let's use that, and now these three zeros and their multiplicity to get a better picture of the drawing. So we can answer this because they were all odd multiplicities. They're all going to cross the x-axis. So let's draw this quick. We had three zeros, minus 9, minus 4, positive 4. We know based on the end behavior it should rise to the right, fall to the left. And we know at each of these zeros it should cross. Put in the zeros, and to fill this in we would say it's going to come up and cross at minus 9, do something, come back down, cross at minus 4, do something, come back up to touch the x-axis again at 4 and cross again, and then match up with its end behavior. So we can get a pretty good sense of what this thing's going to look like. Okay, those are considered kind of challenging. The next two are a little bit simpler, I would argue, because it's just plug and chug. So first we're going to look at what's called the Intermediate Value Theorem. Okay, it's not too challenging, hopefully, of an idea. And it says this. I have two numbers, A and B. So I have two x values, A and B. If I compute f of A, and it's positive, so I calculate f of A. I plug in A into the function, I get a number, and it's somewhere up here above the x-axis. It's positive. And if I calculate f of B, so I plug B into the function, and it spits out a negative number. What the intervenient value theorem states is, the only way to get from A to B going left to right is I have to, whatever I do, I have to pass through the x-axis to get there. So what this means is there has to be a 0 in between A and B. And this works if f of A is negative, f of B is, I can draw it quick. So what if these are reversed? So let's say I plug in A, and I get f of A down here. So now the A gives me a negative number. And let's say I plug in my B, and f of B gives me a positive number. I'm somewhere up here. Then the same idea applies. I can only go from A to B by crossing the x-axis. So there's a 0 there as well. Okay? So that's what the intermediate value theorem states. So what you're looking for is if f of A and f of B have a difference in sign. So if f of A and f of B have different signs, there must be a 0 between A and B. If f of A and f of B have different signs, there must be a 0 between A and B. And the two pictures hopefully prove that. Okay, so let's take a look at this problem. In this problem, they give you A is -2 and B is 0. So we just have to plug those into this polynomial right here. So let's plug in f of A. F of A would equal f of -2. That equals, anywhere I see an x, I replace it with -2. So it's 2 times -2 to the 4th, minus 11, minus 2 squared, plus 2. And if you get this right, be careful with these negatives and powers. If you get all of these correct, you should get f of -2 is -10. Now this is the y value of this x value of -2. Let's try 0. So f of B would equal f of 0, which is 2, 0 to the 4th, minus 11, 0 squared, plus 2. Well, this one's pretty easy. All these zeros to whatever power go away, so you're just left with positive 2. And that's the y value when x is 0. So if we plot this, we had an x value of minus 2, and for that one it had a y value of minus 10 down here. And when x was 0, we had a positive 2 in the y. So our 2 points would be minus 2 comma 10 and 0 comma 2. And the same argument applies. I can't get from this blue dot to this red dot without crossing the x-axis. So there must be a 0 between x equals 0 and x equal minus 2. Okay, so to answer this one, we would just pick the right blanks. So minus 2 was less than 0. So when x was minus 2, the y value was less than 0. We're only considering the y value, so the y value is minus 10. And when f was 0, the y value was 2, which is greater than 0. This one is less than 0. And it's going to say there should be a real 0 between those two numbers. Okay, so a lot of drawing here, a lot of theory, but hopefully it makes sense. You're just trying to get from point A to point B, and you're going to have to cross that x-axis. There's no other way to do it, and so there has to be a 0 there. Okay, if we get all those drawings out of the way and we understand that, then these problems can be pretty quick, because I just have to plug in negative 5 and negative 2 into this polynomial and see if they have different signs. So f of a is the same as the function at minus 5, which would equal, be careful here, minus 5 to the third plus minus 5 squared. I encourage you to try this one on your calculator. Make sure you get these signs correct. Minus 3 times minus 5, and then plus 11. And if you do all of these numbers correctly, you should get negative 74. Now we try f of b. It's the function when x is negative 2. It's negative 2 to the third plus negative 2 to the second minus 3 times minus 2. That's 11. And if you do this one correctly, you should get positive 13. So notice they have different signs, so that guarantees there will be a 0 between negative 5 and negative 2. Now you just have to get the blanks correct. Negative 74 is less than 0. I believe it's a this time. Negative 74 is less than 0. And f of negative 2 was 13, which is greater than 0. And therefore, there will be a real 0 between those two numbers. Okay, 9 and 10 are the hard ones here because they're going to put all this together. So they're going to have us look at absolutely everything. So the first thing we want to look at is end behavior. Get a sense of, is this thing a bowl? Is it an S? Is it up? Is it down? So to do that, we're going to count how many X's we have. So first off, AN will be the number in front. So this is AN. Notice it's less than 0 because of the minus sign. So that's going to affect how our end behavior is going to look. But now count how many X's. You have x squared and x squared. So you're going to get out of this something minus 4 in front, x to the 4th. And so if you go back to one of the first drawings we did, if you have a even power with a negative coefficient, it's a bowl that points down. So this thing should fall to the left, fall to the right. So that's what we expect for the end behavior. And that's going to answer the first question. So the graph falls left and falls right. Now it says find those x-intercepts. Well, to find these, we need to factor this. So we're going to have f of x equals that minus 4. I'm going to write this as x minus 1, x minus 1. So if I have x minus 1 squared, that means I have 2 of those bubbles. Then I'm going to use that same trick we used before. If I have x squared minus 4, which is 2 squared, that will factor to x plus 2, x minus 2. So there's our 4 bubbles. I should have mentioned this. If you have degree 4, then you have up to 4 zeros. Degree 3, 3 zeros. Degree 2, 2 zeros. So we've been kind of seeing that. We've had 3 zeros, and now we got 4 zeros. But let's make sure I make that point clear. So the degree will also indicate how many zeros you can have. Okay, and if I look at this, the zeros are going to be 1, 1, minus 2, and positive 2. So notice I have two 1s. So I have 1, I only need to write one of them for the homework, minus 2 and 2. So I'm going to record that that 1, there's two of them, so it's multiplicity 2. That minus 2 I only had 1, so it's multiplicity 1. And this positive 2 I only had 1, so it's multiplicity 1. I don't necessarily care about the number, I care about even odd. So this one is even multiplicity, so it's going to touch and turn. These both are odd, so at those two zeros, it's going to cross the x-axis. Okay, so we're already starting to get a nice picture for this. Let's see how much we can fill in. We have a 0 at minus 2, we have a 0 at 1, and we have a 0 at positive 2. So let's put those zeros in. We have 1 at minus 2, 1 at 1, technically two zeros at 1, and then 1 at 2. So it should, let's put in the end behavior, it should fall to the left, fall to the right. In between, we know at minus 2, because it's multiplicity 1, it's going to cross. Then it's going to come up here and do something, but it has to come back down to get to the 1. At 1, it's multiplicity 2, so it's going to touch and turn, do something, but then it has to come back down through to cross the 2 and then meet up with its end behavior. So we know it's going to look something like that. Okay, this one says the graph crosses the x-axis at which zeros? Well, it's going to cross at minus 2 and positive 2. Okay, let's see what's next. I want to keep the drawing if I can. So let's go down. So we need this one. So let's try to keep that drawing. We have those zeros. And it's going to say, okay, where does it touch and turn? It touches and turns at that x equal to 1. Okay, now it wants us to put a little more fidelity in, so it says, calculate the y-intercept. The y-intercept occurs when x is 0. So our function was minus 4, x minus 1 squared, x squared minus 4. And if I plug in x is 0 for that, f of 0 will be minus 4 times minus 1 squared, so these x's just go away, times 0 squared, which is just goes away, minus 4. And we're going to get minus 1 squared is positive 1, so it doesn't really change anything. So I just have minus 4 times minus 4, which is positive 16. So we can add a little more fidelity. This crossing point right here is 16 high. Okay, so we'd say 16. Now, does it have symmetry? If it's even, it would have symmetry about the y-axis, so it would be a reflection from top to bottom. Oh, excuse me, not y-axis. It would be a reflection from left to right. Now, this one's close. If these two humps were exactly the same, it might have symmetry, but if it's touching at positive 1, it would also have to touch at negative 1. So it doesn't have y-axis symmetry. Origin symmetry is for odd functions, so it's where it looks like this. And it's symmetrical about these two, about this diagonal. We don't have that for sure. So, because we don't have either of those, we're going to say neither. It doesn't have either of those symmetries. Okay, now the last thing, with all of this, we just have to pick the right drawing. So which picture is it? And my picture is already pretty close. So let's just look at which one matches it the best. And their scale's different, so that's going to make it obviously not look exactly like mine. But we definitely have to fall to the left, fall to the right. This one's rising left, falling right, so that one's out. This one's rising on both sides, so that one's out. And then it's hard to see with my camera window here, but this one is symmetrical and it doesn't quite look right. So this is where it crosses at 16, and you have your -2, and you have your +1 and +2. So the answer is going to be C. And I know there's a lot there. Try to recreate these steps slowly, and reach out to me if you have questions on these. These can be tricky. Okay, 10 is the exact same approach, but maybe a slightly different picture. So let's start with the end behavior. So there's a coefficient of 1 in front, so an, the coefficient is greater than 0. Now you have to count how many x's you have. You have 2 from this term, 3 from this bubble, and then 1 from this one. So you have 2 plus 3 plus 1 is 6. So this is the same as x to the 6th. Now x to the 6th is a bowl, just like the last one, but because this is positive an, it's a bowl that's going to rise to the left and right. So this would be a positive coefficient x to the 6th. Okay, so this one's going to rise to the left and to the right. Find the x-intercepts. Hopefully this one's not as difficult to see. The function, let me write it again since I made it. See? X squared x minus 3 cubed x plus 2. So notice this one, the 0 is 0. So 0 will make that whole thing go to 0. We're saying it's equal to 0. But let's also write the multiplicity. There's 2 of these. So this is multiplicity 2, which is even. So it is going to touch and turn at that point. Let's look at this one. The 0 is 3. Its multiplicity is 3 because of this power 3, which is odd. So it's going to cross at that point. This one, the 0, is -2. There's only one of them, so it's multiplicity 1, which is odd, so it's going to cross at that point. So we already have a pretty good sense of what these things are going to do. So my zeros are 0, -2, and 3. Where does it cross? So the 2 that cross are at 3 and -2. Let's write in order, -2 and 3. Next one's going to ask us which ones touch and turn. Well, the touch and turn are the only ones we didn't write, and that was 0. So 0 is going to touch and turn. Okay, and then they want the y-intercept again. So to get the y-intercept, let's record these zeros because I'm about to clear this out. Our zeros were, well, let me just keep that then. Let's see if we can do the y-intercept. Let's see if I have enough room. So the y-intercept occurs when x is equal to 0. Let's use color to help us here. Let's do this in purple. So the y-intercept is when x equals 0. So we plug in 0 into this function, and we would get 0 squared. Well, look at that. That 0 squared is going to kill off everything, so it crosses at 0. Okay, so let's try to draw it before we look at the pictures. So we know, let me write these zeros over here. 0, it's going to bounce. 3, it's going to cross. -2, it's going to cross. Okay, now I can get rid of all this. Okay, so we know the end behavior is up and to the right, up and to the left. We have a picture that looks something like this. Our zeros were -2. 0 itself, and then 1, 2, and 3. And we know behavior is up and to the left, up and to the right. And we know that it's going to cross at 2, so it comes down here, crosses at -2. It's going to touch and touch and turn at 0, so it comes back to 0, but then touches and turns, and then it's going to come down, and then it's going to go cross through 3 and go back up to its end behavior. So we know that's what the graph should look like. Notice there is no symmetry. So again, it's close. It's pretty close to being symmetric about the y-axis, but these two humps would have to be exactly the same for it to be so. And the correct picture, so you can see it even better, is B. So I drew those humps wrong. B, it should have been, the hump should have come down more on the left than on the right. But you can see better in B that there is no symmetry. Okay, so all those same steps again, and just going through, doing your steps, remembering crossing or touching and turning, all those things, and that will get you 9 and 10. Okay, a problem like 11 is where my students in the earlier class really thought it was a lot simpler. This is, they give you a graph and its end behavior, and you have to decide which polynomial it could be. So notice this one looks like a bowl that points up. A bowl that points up has to have a positive coefficient, and the x has to be even. So just based on those two things, we can eliminate. So any negative exponent's gone, any negative coefficient is gone, so minus 10 is gone, minus 7 can't work. And then the power has to be even, so this x to the 7th is out. That leaves the polynomial, the only possible polynomial this one can be is 12x squared plus 6x minus 10. Okay, similarly in number 12, the last problem, it's a sideways S type of problem, and it's falling to the left, rising to the right. That's the case where an is positive and x is to an odd power. So if it rises left and falls right, that's an is less than 0, and x is odd. But ours is this one, an is positive, so again, we can throw out any negatives, and x is odd, so we can throw out x squared. It has to be the third one. So the only possible polynomial out of these choices, this one could be 5x5 plus 4x squared plus 8. And that will complete section 3.2.